Okay, in this activity, we're going to practice goodness of fit tests, and that is where we are checking to see how well our sample data is fitting what we would have expected. Uh, Here's an explanation of all of that, but that's basically what we're doing here. We've got some notation. O is going to represent our observed frequency. E is going to represent what we would have expected. K is the number of different categories. N is going to be the total number of trials, and P is going to be our probability. We have two different ways that we can calculate the expected frequency. If all the expected frequencies are equal, we would take the number of trials divided by the categories. A good example of that would be if, I've used it several times before, if we had dice and I had each of you roll die. There's 30 students in the class. If each of you roll a die, what would we expect? How many ones would we expect? How many twos and how many threes and so forth? Well, we would take 30, divide by 6, and we would expect 5 of each of those outcomes. So that is a good example on that. The expected frequencies are not all equal. We're going to use E is equal to N times P for each category. An example of that might be if I was going to take a random selection of students here on Ankeny campus DMAC, I would, let's say I take 100 students, I would expect that there's probably going to be more first-year students than second-year students, simply because there's a lot of students here for only a one-year program. And I think that there would be even fewer third-year students. So it's not going to be equal probability there. So we would have some past probabilities that we would probably use in that case. So two different ways. I'm going to do an example of each of these. As far as working through and recognizing the number of categories, I think once we get going with this, we just need to do some examples to get it clear in our head. Requirements. Yes, again, a randomly selected group. Sample consists of frequency counts for each of categories. Each category, the expected frequency is at least 5. The way we set up our HO, our null hypothesis, is a little bit different. We are going to, it's one of two things, which I don't have the second one typed on here, but either it's each of these frequencies and probabilities of rolling a 1, and a 2, and a 3, and a 4, and so forth, they're all going to be the same, or it could be the case where I identify and say that I expect the first frequency is going to be 25%, the second frequency is going to be 40%, third, something else. So I would specify that here if it's something different, an unequal expectation. And then my alternative is that at least one of these is going to be different. If we find that one of them is going to be, at least one is going to be different, that would be a totally different test that you would go into to try to figure out which one is statistically different. That is not something we're going to do in this class. Okay, so we're going to be looking at this test statistic. I am going to do an example where I'm going to do the work for us using this test statistic because I want you to see how similar this is to something we've done before. But otherwise, we're going to go to StatCrunch to find our p-values and our test statistic for the most part. The critical values, I know that in my math lab they're going to ask you to find the critical value. You need to know that StatCrunch isn't going to give this to you. You need to go to the chi-square distribution, and instead of using n-1 for degrees of freedom, we are going to use k-1, and k is the number of categories. So however many categories you have, one less would be your degree of freedom. And then the goodness of fit tests are going to be right tail tests, so we'll move all the way across to the right columns on that chi-square distribution. So in StatCrunch, you're going to go to Stat, Goodness of Fit, and I forgot to identify that you will then select chi-square test. Then within that menu, you're going to identify what column to go to for your observed frequencies and how are you going to identify your expected frequencies. So the best case is just to go ahead and try one. Here we have a table list of wins for 10 post positions over the history of the Kentucky Derby. We're going to use an alpha of 0.05 to test the claim that the likelihood of winning is the same for all different post positions. If they were different, that would be kind of a problem for horse owners. I'm sure they would want to have certain post positions, but we're going to test this out. Okay, so we're going to use this formula. The expectation is that they are all equal. So I'm going to go the number of Kentucky Derby runnings, or yeah, divide by our number of categories. So this N isn't apparently given to us, so I have to count those up. So that came from totaling my observed frequencies to get my total number of N. And then I have 10 different post positions, so I'm going to be taking that 117 divided by 10 to arrive at my expected frequency of 11.7. Okay, so once I've done that, I'm going to follow this chart in executing this formula where I find the difference between the two. For each post, I'm going to find the difference between the observed frequency and the expected frequency. So this came out to be a positive 7.3, and I have a variety of differences here. This one was the largest negative difference, which was negative 6.7, so we've got a range here. So then we're going to take those differences and square each of those. Then I take the squared difference, divide by the expected frequency. This is very similar to what we did when we were doing creating and identifying standard deviation. I just wanted you to see that. So then we would add all those up to get our test statistic. If you don't want to go through all that, which I don't recommend you do, I would say definitely we want to go to StatCrunch. So I have a couple errors here, and I need you guys to help me fix these. I put P of O here. I don't know what I was thinking. We don't start with P of O. Our H of O should start with P of 1. In other words, the first proportion should be equal to the second proportion, to the third, and so forth, on all the way up to the 10th post. Again, please X out the P of O. That is our null hypothesis. Our alternative is at least one is different. If we find that one is different, it's a different ball game, a different problem to figure out that is. You just need to identify that at least one is different. We're not going to specify which one. Okay, so that is our null and our alternative hypothesis. Our confidence level is 95%, alpha is 0.05, and here's my other error. I wrote n is equal to 10, and I should have written k is equal to 10. The number of categories is k. We have 10 categories, so that should be 10. So our degrees of freedom is 9, and I need to go to the chi-square table to find our critical value using degree of freedom of 9 and alpha of 5. So I'm going to go to that. Degree of freedom, I'm going to go down to 9 and across all the way over, because remember, it's a right tail test. I only want 0.05 in the right tail. And that's where we found the 16.919 from our chi-square distribution. So back to our problem. Now we need to go into StatCrunch to do all the work for us. Actually, I want to maintain the test statistic here, so I'm going to go into StatCrunch. Please ignore these two columns here. That is for the next problem I'm going to do. We're going to be working with this first row, which is the number of winnings for each of the post positions 1 through 10. So I go into Stat. I'm going to roll down to Goodness of Fit. I'm going to go over to chi-square. Okay, so my observed frequencies are in this column that is named Post. And then my expected, all cells are in equal proportion. So it's going to calculate that 11.7 for us. So then I just go into Compute, and there we have it. I've got the chi-square test statistic, which is 11.855 is what we had on our form. And then our p-value was 0.1276. And that p-value is pretty darn high. So I'm going to close this down. Again, going back and evaluating our critical value with our test statistic. Our critical value is far out to the right of 13.88 or 855. So that tells us that our test statistic is in the normal range. It's not as extreme as our critical value. Or it can evaluate the p-value. The p is high compared to our alpha of 0.05. So both of these cases would say fail to reject the null hypothesis. So we're going to fail to reject the null hypothesis. There is not sufficient evidence to reject the claim that the likelihood of winning is the same for all post positions. And again, there's like 3 different ways that you could write that. Okay, moving on to the next one. A survey from a decade ago claimed the distribution of reasons why people leave their jobs were as given in the left column. We have limited advancement potential, lack of recognition, low salary, unhappy with management, bored, and need a challenge. Okay, you decide to update this information and survey 200 randomly selected persons who recently left their jobs. This number out of 200 is this number out of 200 is given in the column on the right. So 78 out of 200 agreed with left because of limited advancement potential. 52 out of 200 left because of lack of recognition, and so forth. Okay, so when we're calculating our expected outcomes, they are going to be different based on these percentages over here from our past. So we would expect that our outcome would be the same as it was before. That's what we're testing. So when we do our expected value, we're going to take 200 times these probabilities here from the past to get our expected value. So when I set up my chart this time, I have my observed frequencies, which were given right here, and then my calculated expected frequencies based on these probabilities given a sample size of 200. So this part you would need to be able to calculate. The rest of this I kind of filled in the difference between the observed and the expected and squaring each of those differences, and then taking each square and dividing by the expected frequencies, adding them up. I would not expect you to do this, but I just kind of wanted to demonstrate this again. Also, I forgot to point out we have 5 different categories here. So when we do this by hand, we came up with a test statistic of 2.025, but I need to look for a critical value. So again, I'm going to go to the chi-square distribution, and again, I'm going to be looking at K of 5, so I have a degrees of freedom of 4, and this time I have an alpha of 0.01. So I'm going to go in here, go down to 4, all the way over to the second from the last column, as that is our alpha of 0.01, 13.277. That is how we found our critical values. Again, you have to go to the chi-square distribution to get that critical value. Okay, into StatCrunch. I can close that out because this time. Okay, going into StatCrunch, we would find that I've got the expected, or I'm sorry, the expected and the observed frequencies in var1 and var2. So I'm going to need to go to Stats, Goodness of Fit, our chi-square. My observed frequencies are in var1, and I need to select that var2 has our expected frequencies. Then I click Compute, and I find that, actually I should probably go this direction, that our chi-square distribution matches, or a chi-square test statistic matches what we had when we did this by hand. And again, I don't want you to do it by hand. I think, use the StatCrunch. Our p-value is 73, or 0.7311. So we've got that case where the p-value is high, the null will fly. When we compare the critical value compared to our test statistic, we can see that our test statistic is far to the left of our critical value. I didn't bother drawing those. So I'm sure at the point we can evaluate that accordingly. The one thing that I forgot to do here is I forgot to write fail to reject the null hypothesis. So I need for you to write that in your notes. We are going to fail to reject the null hypothesis because our p-value is high, because our critical value was low. I'm sorry, our test statistic was lower than our critical value. And I guess I did draw the distribution here. There is not enough evidence to conclude that the probabilities for reasons for leaving a job has changed. You might write that differently and say there is not enough evidence to conclude that the distribution of reasons for leaving a job has changed. And again, there's different ways. You just have to kind of pay attention in MyMathLab.